So now we will talk about Rutherford's atomic model. So Rutherford was given a Nobel Prize in order to discover the nucleus of an atom, because he discovered the nucleus of the atom, and an element was named by his name in order to praise him, because he was a very great scientist as he discovered the nucleus, and he also named the proton. So that's why he was a great scientist. So now look at what he actually did. So the setting was like this. First of all, he took a lead box here. This is a lead box. And here is a radioactive substance. It can be polonium or radium. It can be both. No, it will be only one, but he used one of them. Then what he did, he charged the lead plate with positive, because he wanted that whatever the emissions will be emitted out by the radioactive element, that should be in positive. Why? Because electron was discovered at that time. So according to him, he said that the whatever rays will come, so that both will attract, and I will see that what's happening, like is the atom empty, what's, like, he wanted to see the results, like he wanted to observe the atom. So that's why he charged the lead box with positive, and you can simply say it emitted alpha particles which have positive charge, and it's also known as helium nuclei. Okay, then there were a lot of atoms, like he took a gold foil of 0.00004 centimeter. But now over here I will just take one atom in order to explain you guys. So this is the nucleus, and this is the whole atom of the gold. Okay, there's a question that why we are using gold here, not an other element. Because gold is a soft metal. Gold is a soft metal, and it allows good penetration power, and most importantly, it is unreactive. It doesn't react. That's why we are wearing this for longer periods of time, because it's unreactive. It only reacts with aqua regia, AgCl3. We will talk about this another time, but gold is very unreactive. So he wanted to see that if he will be using another atom, so maybe that one atom may react with the alpha particles and form another thing. So how he will observe that what's happening inside. So that's why he used the unreactive metal. So here he used a zinc sulfide plate. There was a photographic plate which he coated with zinc sulfide. Okay, now what happened, there were only 3 conclusions of this experiment. When he passed the alpha particles, most of them deflected, most of them were undeflected. Sorry, as you can see over here, they are undeflected, but some were deflected too. Like this, you can see over here. Over here, and very few little were bounced back. So you can see that many of the alpha particles were undeflected. Like, why? It shows that the atom has the major part of atom is empty. No one which is undeflected, which means the major part of the atom is empty. That's why the reason why they didn't deflect it, because it is empty. If there will be anything, so they will obviously do something else. But there's nothing, they're empty, so it's undeflected. Now, so very few, like 2 to 3 particles deflected. Why? Because they were near the positive charge. As you can see that they were near the positive charge and they repelled each other like this. This is the nucleus and it's going like this because it's repelling it. So, and very few, like 1 or 2 who rebounced, or you can say bounced back. Bounced back. So what's the reason behind this bouncing back? That this is for example the nucleus, and when we hit the alpha ray to the exact midpoint, to the exact point of where the positive charge resides, it repels like this. Why? Because the alpha particles also have positive charge and the nucleus inside is also having a positive charge, so obviously they will repel. Here it was going near, so that's why it deflected on the large angles, and here it was on the exact point, that's why it bounced back. So if you want to see here, so like we have to find the diameter of the nucleus. You can see the line from here to here is the diameter of the nucleus. This is the diameter of nucleus, and you can easily find the radius of the nucleus from this too.